So welcome to the 2016 NASA Ames Summer Series. When going camping for a day, when you go camping for a day, you get up maybe the night before and you figure what you need to take, the food, the drinks, music, whatever you need, you pack in the car and go for a day trip. When going for a week, well, that's a little bit more difficult. You start thinking, what do I really need to take with me? And in all those cases, if you're close to society, a restaurant, or anything like that, if you forgot something, you could just go and get it. But what do you do when you go on a trip that lasts a year or 2 or 3? How much stuff do you take with you? The concept of on-demand manufacturing, on-demand production, sort of like the Jetsons, is really critical when you do long-term trips. Today's presentation is entitled The Future of Making Things in Space, and will be given by Mr. Jason Dunn. He is the Chief Technology Officer and co-founder of Made in Space. And as you guessed it, they're the first company to have a 3D printer in space on the International Space Station. He's working with NASA to enable in-space robotic manufacturing and assembly of small and large space structures. And they are located here on the campus of NASA Ames Research Center. He serves on the UCF College of Engineering and Computer Science Dean's Advisory Board, the Advisory Council to the Waypaver Foundation, and on the Board of Directors for the Future Space Leaders Foundation. He earned a Bachelor's of Science and a Master's of Science in Aerospace Engineering from the University of Central Florida. But the last point is that the company, he and his co-founders in 2014 were recognized by Forbes on the prestigious 30 under 30 list for manufacturing. So please join me in welcoming Mr. Dunn.
Thank you, Dr. Cohen. I appreciate it. Hi, everybody. I'm going to just switch over the slides. All right, how's everybody doing? You hear me okay? So I understand there's quite a bit of students in the crowd. Just show of hands, who's intern or students? Okay, quite a bit. All right, so you're all going back to school pretty soon? Great. Well, hopefully today can be educational. I'd love to just share kind of the views of why we started Made in Space and what we're doing. And we'll use that more or less as a lens to look at what the future of making things looks like. And that's really kind of at the core of Made in Space, is thinking about the future of making things. And we believe that that future is in space. Primarily that space should be thought of not just as a place to have really amazing scientific discovery, but also as a place for business and for industry and for making things. And that's why we started Made in Space. So I'll start with maybe kind of putting things into perspective. That's us. We maybe sometimes forget this when we're working on big space missions and thinking about how do we go back to the moon or go to Mars. But we're all in this together. We're all in that little spot on the planet, all here together, thinking about how to solve big problems for going to space. And for me and for us at Made in Space, we think a lot about our home planet as we design things for making things off of the planet. So to try and capture today's talk and for you to have some takeaways, I like to always point out these 3 things. And this is how we've driven the development of our company and the way we think about what we do. It's making sure that you're doing meaningful work. That's really important in life. To innovate disruptively, and that's a really good key to success, and I'll talk about what that means. And then the idea of starting small projects, but having big vision. And so hopefully these 3 points can stick with you as you go through the talk with me, and you can notice how we've done that at Made in Space. So part of doing this, and for myself, I like to ask really, really big questions that help drive our focus. And one of the biggest questions that drives the thought of making things in space is really comes down to this one question of, is a planetary surface really the best place for our advancing industrial needs? Today, all of our industry exists on this planet. Should it always be that way, or should one day it be off of this planet in space? And is it better suited to be off of this planet? So that's a driving question that we are always searching for answers to. And when we think about what we've done in space, we've done some amazing things. We've sent people to the moon, right? We've built vehicles that drive across the lunar surface. When we started this company, it was things like this that brought my co-founders and I together. It was us asking big questions to each other. Why haven't we been back to the moon in our lifetime? And like the co-founders and probably a lot of you in the room's lifetime. Why haven't we put people on Mars yet? Why are there only 6 people at a time, more or less, living off of planet Earth on the International Space Station? Why isn't it more people, right? You all know this number pretty well, but most people around the world are shocked when they find out that for the history of space exploration, for over half of a century, only 555 people have actually gone to space. That's really not a lot of people, right, when you think about it. And the reason why comes down to a lot of what Dr. Cohen was saying. Today's version of exploration is a lot like a camping trip. It's a lot like the goldfish in the fishbowl. That's how we go to space today. We have to bottle up a little bit of Earth, and we put an astronaut in that little bottle of Earth, and we send the little bottle elsewhere in space. So it's a camping trip. We have to bring everything we need with us, and if something goes wrong, we have to create an emergency fix, or at worst case, abort the whole mission. Think about Apollo 13. So when we started this company, we were thinking a lot about how do we solve that problem? How do we make it so people can live off of planet Earth, independent from Earth, be able to be sustainable wherever we go, whether it's Mars or the moon or in free space. And the more we thought about that problem, the problems of sustainability, the problems of making it safer to live in space and more enjoyable, the more we realized that space, that when we solve those problems, we're actually looking at how to solve similar problems we have on Earth. Because life on board a spaceship is not unlike life on Earth. It's just that we're making all the systems Earth has much smaller. And when we think about life on board a spaceship, we realize that all of us already live on a spaceship. Earth is a pretty good spaceship. And the only difference is most of us have never left the ship, right? And that's what we want to change. We want more people to be able to leave the spaceship. So I'll tell a quick story that helps encapsulate how Made in Space has been trying to solve this problem. And it's one of my favorite stories of what we've done. The story starts with astronaut Butch Wilmore. So Butch was the commander of the space station in the fall of 2014. And the interesting thing about the fall of 2014 is that's when Made in Space and NASA sent the first 3D printer into space. So Butch was one of the astronauts on board when the printer arrived. And he ended up being the first person to use the printer. So if you check his Wikipedia page, it now says that Butch was the first person ever to manufacture off planet Earth. And that makes him one of my favorite astronauts. So we did a lot of really interesting things with the printer. And I'm going to tell you one specific story of what we've printed. And it all came down to one day. We're operating the printer from a little mission control room that's not far away from here at Made in Space headquarters. And we're constantly on the loop, talking to NASA, listening to the astronauts. And we had just printed a tool head, a crowfoot wrench head that would go on the end of a wrench on a tool. And we printed it, and Butch takes it out of the printer, and he says over the loop, wow, if I had my ratchet right now, I would try this tool out. And later on, we were talking to NASA, and they had mentioned that sometimes astronauts misplace things, and we were thinking, well, how can an astronaut misplace a tool? Like, that seems like a really important thing. How do tools go missing? And this happens quite frequently, and it takes a lot of time to figure out where could the tool be. And we're thinking, well, how could they misplace a tool? And then we look at pictures like this one, and we realize that the space station is actually a very cluttered place. It's not that sleek-walled 2001 Space Odyssey space station that we all dream of. It's, in fact, very cramped and cluttered. There's spacesuits. Maybe an astronaut lets go of the tool and turns around, and it floats away inside of a spacesuit or gets hidden behind a tangle of wires down in the bottom. So nonetheless, tools go missing. So that was a perfect opportunity for us to think about how could we make Butch a tool. So what the printer looks like is basically maybe the size of a small microwave oven. It's really designed and optimized for the space station. And to Butch and to the astronauts, it's this like magic box where we control it from the ground. And whatever we build, they open the door and it's inside. They take that thing out. They close the door, it's an empty box, and the next time we call them over to remove something, there's something inside. So for them, it's this excitement of the magic box, and every time they open it, something new is inside. The last time Butch opened the box, he had the tool head, and he said, I wish I had a ratchet. And he closed an empty box and left. And we had about 5 days until the next command window to operate the printer. So working with NASA, we designed a ratchet. NASA gave us the kind of requirements. They said, it has to have a real ratcheting mechanism, which means, a leaf spring and a gear. It needs to have no assembly required. Butch should be able to reach into the printer and take out a functioning tool. So it has to have moving parts but no assembly. And more than anything, it has to be safe. We have to qualify it through NASA safety review. So we got to work, and in one day we designed the tool. We designed it in CAD software. What's really incredible is that while this tool could exist here on Earth, in the bigger picture of why manufacture in space, it never really has to exist on Earth. It only has to exist in software and in space. So that's an important point that I'll come back to later. But for this tool, it exists here on Earth. And we have printers in our lab that are identical to what's in space. So as we design the tool, we constantly are printing prototypes out and making sure it will work. And by the end of the day, we had a tool that worked. It passed all of NASA's requirements they gave us. We had iterated on that tool many times in the lab. And we took the tool, we shipped it to NASA for a safety review. They got it the next day. And this was the first time that NASA would hold a tool in their hand to certify to go to the space station that wasn't really the tool that would go. It was a representation of the tool. The only way that we would make the real tool is to print it in space. So we said, trust us, it will come out in space just like it came out on the printer in the lab. So we went through what you can imagine, a lengthy safety review process, and it was certified for what we called digital launch. And this was the first time in history NASA would do that process. And so it was really amazing for us to see that happen. Once it was approved, we're about day 5, and it's time to print the tool. So it starts in our mission control room. It's a nice small little room with a couple computer monitors and software that NASA installs on the computer to allow us to communicate to the 3D printer. So it's a lot like a remote desktop to space. So here we are taking the digital file and sending it through the NASA system to space. It first goes over to the Payload Operations Center in Huntsville, where then it's uplinked to the space station. And when it gets there, it's installed on a laptop computer, and in the image, it's the laptop in the front of the screen. So NASA installs the file there, and then once it's there, they say you're cleared for printing. Inside this glove box is the printer. If you remember the image of the printer, you can see it right here, there's the printer, and this right there is our electronics and power supply. So it's inside of a glove box because this first printer was a science experiment. We were trying to figure out what would happen if you 3D printed in space, so keeping it behind a glove box and with some levels of containment was really important. So now we're ready to print. We take over, we send the file to the printer, we hit print. It takes about 2 hours for that tool to be printed. 2 hours later, it's printed, and We call Butch over. We tell NASA it's ready. Butch comes over to remove the part. Here he is opening the door. Remember the last time we even heard from Butch, he had mentioned that he wished he had that tool. And he went off for 5 days working on all the other things that astronauts do in space. And he left an empty box, and he came back to open the door. No idea what's inside the magic box this time. And then this is the picture immediately after he removes his ratchet. I like to call this picture Happy Butch. You can imagine the surprise on that he's going through when the thing he asked for 5 days ago is now in his hands. And that went down as the fastest anything has ever gone from design concept to being in an astronaut's hand in space. Nothing has ever been sent to space that fast. And had Butch been on Mars, the story I'm telling would almost be identical, right? The way we designed the tool would be very similar. Even if it were a different manufacturing process, if it were metal 3D printing, it would still be really a similar story. And definitely the way we went through a safety review and then sending the information to a printer. So what we did was NASA and Main Space demonstrated that you can get hardware into space very, very quickly with this technology. And that was the really important part about this story. The tool itself was brought back to Earth. It's gone through a lot of really amazing analysis at NASA to understand the properties and compare it to what it would be like if it were printed on the ground. So that's a really good story that explains kind of how we're thinking about manufacturing in space. I'd like to walk you through how we got to this point. How did we even get to the point where we could put a 3D printer on the space station? It's a different type of device, right? So it started in 2011 here at where we were setting up our office in the research park at NASA Ames, and we won a contract through the Flight Opportunities Program, which was run out of here at NASA. And through that, we were able to take 3D printers into zero gravity. And this is definitely one of the most fun parts of the job. And if any of you ever get a chance to go into zero gravity, I highly recommend it. So we had, through the summer of 2011, we flew on this parabolic airplane 10 times, which is actually quite a bit of a flight, right? Flight data. So every flight, every one of those 10 flights, you get about 40 parabolas, and each parabola is about 20 seconds of zero gravity. So we started out by taking some commercial 3D printers, as well as some ones that we designed ourselves into zero gravity. The hope was that a commercial 3D printer would work, because if it did, then it would make our jobs a lot easier. All we wanted to do was put the printer into the space station. Right off the bat, we found out that the commercial printers they don't work. The issues go from the mechanical, they're designed with gravity in mind to hold things in place, belts and pulleys and build platforms, to things like the thermal conditions. We're well aware that hot air rises in this room, and that's because of the buoyancy effect that is only there because of gravity. But if we move gravity, we remove buoyancy, and now hot air doesn't rise through natural convection, and we have to create forced convection and other means of thermally controlling things. In 3D printing, it's very much a thermal process. So you have to keep hot things hot and cold things cold and keep that uniform. So we had to do a lot of work to figure that out, so that we not only can print, but we get a print that's reliable and as robust as something you might find on a ground 3D printer. So we did a lot of this work. What was really amazing for us is that we flew those 10 flights. The first flight, nothing worked. The second flight, we were trying out different things, building new experiments. Every single night, we would take our experiment out of the plane, change it, make it in the hotel room, try to make it better, then fly it again. And we would come back every 3 weeks to fly again, and we were going in Houston. We were there on the very last week of our Flight Opportunities campaign in September of 2011, and we had 4 flights. We did the first 3 flights of the week. We learned a little bit, but we still didn't get the printer to work, and we were down to literally the last flight of the last week of our last chance to ever figure this out, and we made the last bit of changes we could come up with, and it worked. And it was this amazing moment where some people may have given up after the very first flight and seen that it didn't work, and we just kept going the whole time, and it got all the way to literally our last chance to make it happen, and we figured out how to make a printer work. And this video, that image is actually from a later test flight where we actually took the 3D printer that was going to the space station into the flights and tested it out. Because of that, we were able to then go back to NASA and say, we know how to design 3D printers that can work in the space station. We started to do that with NASA to design the printer and build it for flight. So it's one thing to make a printer work in zero gravity. It's definitely another thing to make one work that meets all of the requirements in terms of safety and operational requirements for the space station. So that's why it ends up looking like a very different type of machine. So I'll just maybe briefly talk about why it's important to have the printer there. Well, we've done a lot of different types of prints now. Different astronauts are getting to enjoy it, and they mention that this is one of the most fun activities they get to take part of. But the reason why a 3D printer is so important is because the way we do space, like Dr. Cohen said, is a lot like a camping trip. We bring everything we need with us. So there is a lot of redundancy, a lot of spare parts in space right now. There's entire modules filled with bags that have spare parts in case something goes wrong, if we have to fix something and we need the spare part right away. There's also a lot of waste. There's some of these duffel bags here might be filled with garbage. So we have volume that would be really useful for science experiments or research, but instead it's being used for storage. And if we think about a journey to Mars, we really need to move away from this paradigm and get to the point where all of our space is being used efficiently. And if we have a 3D printer, all we have to do is have some material feedstock and the printer, and we can build the things we need when we need it. And then the other piece of the puzzle that we're working on in the company is a recycler. So you can take the parts when you're finished with them and turn them back into filament. We call that redo. So it allows you to redo something with your printed parts. But the interesting thing is that it also lets you take plastic trash and turn it into a filament, into a 3D printed part. So today, when there's not a 3D printer to use in space, the astronauts are forced to use the other things they have available. One of the most fascinating stories was when Sunita Williams was on a spacewalk and had to fix part of a power supply and resorted to building a new tool using her toothbrush and some duct tape. To be able to fix something as important as the part of what's delivering power to the space station. So I'm going to just kind of explain why are we not doing this? Why are we not manufacturing space enough? Well, it's important to understand where we've been, right? Yuri Gagarin, the first person to go to space in 1961, launched on the pinnacle of technology of the time, the Vostok rocket, out of the Baikonur Cosmodrome. Now we fast forward a half a century later to someone like Butch Wilmore, and how does he get to space? Well, he gets to space on none other than the Soyuz rocket. They almost look identical, and the reason why is because it's almost the same technology in many ways. The Soyuz was flying only 6 years or so after Yuri's first flight. And even if we look at other ways we've sent things into space, space shuttle, maybe Apollo, they may look different, but it all comes down to chemical propulsion. We're using the same basic technology to send things into space as we always have. The Apollo astronauts had to travel 10 times the speed of a rifle bullet to escape the gravitational pull of Earth, and that's because it takes a lot of energy to get off of this planet. And that's why only about 2% of a rocket is the thing we want in space, and the other 98% or so is the fuel and the rocket and the structure and the engines and so on. So it's, there's not a huge margin of the thing we want in space compared to the rocket. So we look at it as the supply chain problem. The supply chain to space is broken and it should be fixed. Today, the supply chain looks like rockets that get put on barges and shipped across oceans. Some rockets have to fit onto trains to move to the launch pad, which means everything that we put into space, first of all, has to fit into a rocket. So the size of things in space are constrained by the size of a rocket. And the size of a rocket, in some cases, is constrained to the width of a railroad track. So think about how funny that is, that the requirements on the width of a railroad track dictate the requirements of the size of the things we have in space. And that is a broken paradigm in our mind. It makes the cost to space extremely expensive. A liter of water could be $10,000 in low Earth orbit. So while other people were looking at how to make a rocket better, more efficient, cheaper, reusable. We asked a different question. We asked, what if things didn't have to be launched from Earth at all? And what we're looking at is this idea of disruption, that if you could, entire disruption from rockets. And I'll explain quickly what I mean by that. When I say disruption, I mean the definition from Clayton Christensen, which I'll read out loud, is a process by which a product or service takes root initially in simple applications at the bottom of a market and then relentlessly moves up market, eventually displacing established competitors. So I'll give you an example really fast what that means, but notice that a disruptive innovation usually is very different than the incumbent. So the example is the spice trade. We all have heard of the spice trade, but how many of you know why did that exist? Why were we trading spices? Does anybody just call it out if you know why we traded spices? What's that?
Preservation of food.
That's it. So most people don't know that. We were using spices to preserve food. Spices were, in a way, a technology of food preservation many, many years ago. And the reason why was, well, we didn't have modern-day technology to preserve food, but it's not like spices made food last longer. It just made rotten food taste better. But it was good enough for people to use it, and there was an entire industry of shipping the spices around the world until one day a gentleman named Frederick Tudor, living in the Massachusetts area, I believe, saw a new business opportunity. You see, the lakes in that area would freeze over in the winter, and people would cut the ice off of the lake and use it for a type of food preservation, but it would melt very quickly. One day, Frederick Tudor goes to the Caribbean, and he notices how hot it is, and he thinks, wow, if they could have this ice that I get in the winter, it would really change things here. So he went back home, and he designed a device to keep ice cold. He became known as the Ice King, and what he invented was ice houses, these giant insulated buildings, and they would harvest the ice in the winter, fill up the houses, and then sell it all throughout the year and even ship it around the world. Some of the biggest ice houses ended up being built in India. So the spice trade was 100% disrupted by the ice trade. And what's important to notice is that the people who were working in spice trade probably were not the people who then transitioned to ice harvesting. An entire industry of spices got disrupted by something new. And that's not the end of the story. Then there was the invention of what was called artificial ice. And it took a long time for artificial ice to catch on because people didn't believe it was as safe as natural ice from a lake. But eventually, this technology of creating ice became the new norm. And then there was ice delivery and these little boxes that your grandparents had that ice would get delivered and you'd put it in this little box, and it's about the size of a mini fridge today. And that's not where it ended. Then there was the invention of refrigerators and being able to make ice or just have refrigeration in your home. So once again, the delivery of ice gets disrupted by this. And now today, refrigerators are real fancy. I just saw this one recently that has a touch screen on it, and you can send notes to people, and it looks like there's Evernote on there in case you want to write down a good idea while you're cooking. So the question to ask if you're in the refrigerator business is this really where it ends? Did we go from spices all the way to this point where we could have the touch screen on our refrigerator? Or is there another disruption coming? Does the refrigerator get disrupted by something? And the answer is probably yes. Now, to bring it back to space, if it weren't for refrigeration, we wouldn't have liquid fuels for our rockets. So in a way, maybe the spice trade is part of what helped us get to the point where we could launch things into space. So we asked a different question: what if you didn't have to launch anything at all? And our vision means that you can build things in space that are far bigger than a rocket. You could build antennas the size of football fields that could provide global broadband internet anywhere on Earth. And what matters, though, is what we build, not how we build it. The machine is a machine, but what we build is what's really important. And a little example there is when New Horizons was sent to Pluto, it captured award-winning photos of Pluto that we'd never seen before. when it launched 10 years ago, some of the software didn't even exist to capture these images. And the software team on the New Horizons actually worked on their software for 10 years. And as new advancements in software came out, they updated and sent the updates to the spacecraft. And that's how we got these images. So they were able to send the digital code of software to the spacecraft years after it launched. And that's what we're doing with hardware. We can send the machine into space, not even have to know what it will build for many years, and then send the digital information when we need it. So now that we learned how to do that with the first printer, we launched another printer into space called the Additive Manufacturing Facility. It's really a platform, and it's open for anybody on the planet to use. So it's commercial. That means that anybody in this room can use it, anybody on the world can use it, and they do. So we also open sourced the code that allows, or open source the interfaces so that people can design new hardware that goes on that. I'll play a quick video of one of the people using the printer, which I enjoy. So this is our partner at Lowe's, the home improvement company. So that's one of the people who have used, and one of the groups who have used the printer that's in space today. Lowe's printed this tool for astronauts. It's one of their branded wrenches, but it's specially designed for some applications on the space station. So now that the printer is there, we're doing all kinds of interesting things, and interesting users are coming out to us with their ideas. One of my favorites is, how do you build satellites in space? This is today how a satellite is built. They're big, they involve clean rooms, lots of manual touch labor. Now we have, with CubeSats, the ability to make really small, easy to build satellites, and small teams can do it. We have university groups coming to us with their designs of satellites that take some parts that are built on the ground and launched into space, and then other parts that are 3D printed. And we can really quickly assemble a satellite in space and deploy it. So imagine, this is right down the road when we do this. Very soon, satellites will have been built in space just like they've been done on the ground. And what does that mean for the future of satellites? Here they look when a satellite is launched from ISS. The other is exercise. Today, exercise is a very intensive part of astronauts living in space to keep up muscle tone and bone density and so on. One of our partners is Dr. Yvonne Kagel. She's an astronaut, and she's developed some really interesting medical applications so that you can reduce the amount of time needed to exercise in space by using these tools. And it turns out that the tools can be 3D printed for the most part, and everything else is a found item on the space station. So there's no need to launch anything. You 3D print some, go get the rest from found items. So I said earlier, what matters is what we build and not how we build it. The printer is a magic box. What matters is what comes out of it. And there's a parallel I'd love to explain. These are the women of Apollo. Most people don't know the story of the women of Apollo, but they were really the ones driving from the back end, making sure we could send people to the moon and bring them back safely. It's people like Katherine Johnson, Margaret Hamilton, who their job was computer. Like their profession was a human computer. And this was at a time where computers were too big and too expensive for everyone to have one on their desk, so people did the math. Catherine, Medal of Honor winner from the president, did the math to figure out how to send astronauts to the moon and bring them back safely. And then people like Margaret were writing the software code out from that math and putting it on the spacecraft. So there was a time when computers were a profession, when people were computers. And we obviously know how that changed, right? Now we all have computers in our pocket. It used to be that an entire room of people did the computation that is not even anywhere close to what the computer in your pocket can do. Today, though, the way we design satellites is very much a manual process. It takes entire rooms of people and huge cubicle farms to do the design work and to create the satellite. What that means is that everything we put into space is limited by, first of all, the capacity of what our human brain can imagine, and the capacity of what two hands, one on a keyboard, one on a mouse, can manipulate on the computer. The computer itself can do far more than what we are able to manipulate the computer to do. So where we're headed is software that actually does design for us. And we use the software to have it give us the most optimal solution. And these are often called optimization software, generative design, evolutionary algorithms. But what we're working on is the ability to give the computer the operational environment. I need 2 satellites connected by a very large truss, or I need an antenna the size of a football field, and it's going to be in low Earth orbit, and this is the loading condition. You don't give it a design and say, make this design better. You literally give it the environment, and you ask it to give you the most optimal design. And it runs through algorithms, and it comes back with maybe thousands of options, and you narrow it down, and you decide which one makes the most sense. So we're headed to a point where the engineers, and I'm one too, so I think a lot about this, become the mentors to the machine. We use these machines to help us engineer better. What that means is that we could be very close to a point in time where instead of a giant room of cubicles of people designing things, any one of you with this software can do what used to be done by thousands of people. And that's an incredible power, because imagine when everybody in that giant room of engineers all has this power, what will we create next, right? So we're working on, once again, the machine that can build those things. It's called Archinaut, Architecture Astronaut, and it goes into space. It's a spacecraft, and it builds really, really big things. It uses 3D printing, it uses robotic assembly, and it launches some things that can't be built in space and assembles it into the structure. So it allows us to optimize designs in software that never have to exist on Earth, send the information to Archinaut, and have it build it there. And to us, that's really incredible, because that means that maybe a satellite in the future that today looks like something that we can build by our own hands and put into a rocket, one day will be far different. A ComSat may not look anything like a ComSat in the future when Archinaut can build it there. So what we've done as a company is we've taken something from product, the first 3D printer. We built a platform. Now everybody can use it, and that same technology builds new capabilities like Archinaut. But at the end of the day, what matters is not just the idea of manufacturing, but this concept of processing. Everything we're doing with made in space and with manufacturing in space is basically processing things in a new way. We have this new environment to process things. So I'd like to explain how new processes unlock new industries. The first story is the story of 17th century England. Birchwood forests were being completely decimated. And the reason why is the wood was being used to burn for energy to support the industrialization of England. But they were running out of wood. They knew that in these water-filled mines was coal. And if they could get the coal, they could use that for their energy, but there was no way to get the water out of the mines. And then a gentleman came along, Abraham Darby, and he invented a new process. He invented the coke oven. And it was essentially an oven that got to really high temperatures that allowed the formation of coke to be created, and the coke was used to make steel. Once you have steel, you can make pumps, and once you have pumps, you can get the water out of the mine and get the coal. And once you have the coal, you can either burn it in the coke oven and make more steel, or you can do other things with the coal. So this new process of the coke oven, in fact, was the beginning of what we call the Industrial Revolution, the machine age. All of the things that built the foundation for all the technology around us came from this one new process of unlocking the abundance of steel. Another great example is comes to this picture. What do these, just yell it out, what does all these pictures have in common? Exactly. So it's aluminum, right? Everything from the space shuttle to something we can crumple up and throw in the trash exists because we have abundant aluminum. And what's surprising is that aluminum wasn't always like this. It used to be one of the most precious metals on Earth. It was Napoleon III fed the King of Siam on aluminum utensils and aluminum platter while his people ate off of gold. So aluminum was more expensive than gold. The tip of the Washington Monument is made of aluminum to signify that. So how did aluminum go from one of the most expensive rare materials to something we throw away? Well, once again, it was a new process. There was kind of invented by several people around the same time, one of which was Charles Hall. He's a pretty young guy. He's at Oberlin College in Ohio, and his chemistry professor says the first person to figure out how to make cheap aluminum will be very wealthy. And he goes home, his sister's a chemist, and together they figure out an electrolysis process to unlock aluminum from fluoride salts. And electrolysis, that process, is what makes aluminum so abundantly available for us today. So the question is, what new processes might we create in space? How can the space environment allow us to unlock new processes that don't exist on Earth? We have access to microgravity, also controllable gravity. You can spin anything up if you wanted to and have any gravity you want. You have the radiation environment of black body facing away from the sun. You have the temperature extremes you can get from being in and out of the sun. Is range. There's all kinds of interesting things. The resources that are out there are so much more, obviously, than what we have on Earth. So there's a lot of really interesting things that space allows us to do that we can't do on Earth. And that really is the future of why we should be bringing industry into space. So I'll give one example really fast of what Made in Space is doing there. So we think a lot about how to make things in space, like 3D printers that are there to build things, and Archinaut that builds big things in space. But we're also thinking about how do we make things in space that can't be made on Earth and then bring them back to Earth. We announced a project recently, it's a flight mission, that will make optical fiber in space. And this is something that we have optical fiber on Earth. This is a specific type of fiber that if it's made in zero gravity can be 10 to 100 times better than the fiber being used on Earth. And it's simply because in the pristine microgravity environment, we can make a better type of fiber. So what we believe is that we need to start to find products that can be made in space and brought back to Earth. And in the beginning, they may serve like niche markets. They may be very expensive to buy on Earth, but there'll be markets for those. And the moment that happens, the moment we bring things back to Earth, the more people will realize the benefit of doing that, and we'll start to see new things happen. Transportation coming back to Earth as available as transportation going into space. So I come back to the spaceship and to this thought that we all live on a spaceship as well. And as much as I believe personally that we will go on to go to Mars and to build habitats on the moon, and my favorite, build giant colonies in space like Gerard O'Neill imagined, I also recognize that we've got it pretty good here on Earth. Like this spaceship's treating us really well. It wants to keep us alive much more than space wants to keep us alive, and we need to respect that. We need to respect the fact that this is a really interesting place in the universe as we know it. So as we talk about these things, I think it's important to have the discussion about changing the world and not just about changing worlds and going to other places in space. And we need to have that discussion because we aren't currently doing the best we can. Like, we can admit that. The industrialization of our planet has a dark side. We have to, to abide by the second law of thermodynamics, we have to radiate our heat from our processes into the atmosphere or into the oceans, and as our heat sinks. In space, your heat sink is abundant and it's just the universe, and you don't pollute that. So we need to be thinking about that. We need to be thinking about today how we turn mountains into holes in the ground to get our resources, and one day we will run out of mountains to turn into holes in the ground, and we will evidently transition to getting those resources in space. So when I asked that question that I asked earlier, is a planetary surface the best place for our advancing industrial needs? Perhaps today it is, but in the future, at some point, it won't be. That's the belief I have, is that one day it won't be. And to get to that point, there's no reason we should delay. There's no reason we should say, we'll just wait until we have to go there and then we'll go there. Like, there are things we can do today better off of planet Earth than on planet Earth, and we should start with those things. So I love this quote, and I'll leave on this. Perhaps the original pale blue dot speech, but that remembering that we all live on this fragile rock in the solar system, and we should do everything we can to protect it while exploring space and finding new places to live. Thank you.
Very good. Thank you very much. We should talk afterwards. So we have time for a few questions. If you have a question, please raise your hand. Wait for the microphone to come to you. Stand up, ask the question, and you'll get an answer.
Thank you. Very interesting talk. But one question that you mentioned, that you are planning to build the big structures in space. That to do this, you need not only the technology, but you also need the raw materials, and a lot of them. So it's not a problem with these small tools, but if you're going to build something big, where would you get these raw materials?
Yeah. It's a wonderful, wonderful question. Where did we get the raw materials to build the things that we want to build? So there's a few parts to that answer. The first part is that today we launch them from Earth. If it's the printer on the space station, we launch the materials from Earth. And the benefit there is that if the thing that we're building only has to survive in space, in zero gravity, let's imagine the structure of a satellite. It doesn't have to survive launch. It doesn't have to even exist in one gravity in a clean room. So the amount of material needed for that structure it can be less than the amount of material for the structure if it were built on Earth and launched. So that means that if we launch raw material into space and then build the thing we need, that material goes a longer way than had we just built the thing on Earth and launched it. So we start there, and there's just right off the bat improvement. Next step is what we call in situ resource utilization, ISRU, using the resources that you have in space. Now, most people think about the asteroids or maybe the moon as the resources. We think about other resources that may exist near term. So I mentioned earlier we're building a recycler. It goes into the space station. It takes plastic waste that's already there and turns it into material. So there's actually already a lot of material in space that we can reconstitute into raw material for the printing process. Now, when we get to the thing I think you're asking about, how do we build the very, very big things, the things that may require so much material that you wouldn't launch it because it would still take many launches. Eventually, we will need to get resources from space. We think that is many steps down the road, and to build a business, we start on the things that there are markets for, but think about building those markets towards the time when you need the resources. If you're really interested in it, we have a NASA NIAC, which is an innovative advanced concept project looking at that problem. And what we're looking at is how do you move an asteroid resource from, let's say, the asteroid belt to a location of interest where maybe mining happens. And we came at it from a completely different angle where we turn the asteroid into a spacecraft and have the asteroid fly itself to that location. So you can look that up, and it's pretty interesting.
These are wonderful thoughts. Is this a thought?
There's wonderful thoughts, but what is your timeline? When is this going to happen?
It's specifically what, I mean, we have a printer in space today.
You have a
that's
printer,
operating.
but you're going to build large structures. How soon do you think that's going to happen?
Yeah, that's a good question. So the program with NASA to do Archinaut is a public-private partnership between Made in Space and NASA, and it's through a new program they have called Tipping Points. And Tipping Points is specifically looking at programs that if NASA funds today, in the span of 2 years or so, can get beyond a tipping point where no more government funding is needed. It can go straight to commercial markets. So the Archinaut program was awarded that contract under tipping points, which means that in the very near term, let's say 2 to 4 years, we are introducing real products into the space market of building big things in space. So it's pretty quick for us. Yeah.
Yeah, I have a question. You mentioned this issue of cost. There are a number of issues that you bring up that are really interesting, one of which is where are the resources coming from? But there are other issues as well. We know, for example, that the human body is so poorly adapted to space that people don't survive in space. I mean, we can keep them alive, but it takes incredible amounts of money and energy to do that. And their bodies are deteriorating at incredible rates. Endocrine system, bones reabsorb, muscles go away. And what you're describing is something that is sort of far-fetched in terms of how are we going to utilize this environment in a way that's both economical and reasonable. So I'm curious in terms of your timeline and in terms of your plans, why you think this is better, also given that Spaceship Earth is really in need of the kinds of technologies that you're talking about.
Okay. I think there might have been a couple questions there, but the explorer in me, and that's part of like the driving force of why I do what I do is exploration. The explorer in me wants to be able to go, and I know a lot of people do, and they'll say I'll go, and maybe my body can't handle it for very long, but at least I get to go, right? And I think that will always exist. There will always be people who want to go because it's this part of our brain that wants us to explore and say what's on the other side of that mountain, what's on the other side of that ocean. I think that will always happen, but and that's a very important part of why we do what we do, so that as people go, they bring tools with them that they can build the things they need, and it's safer, right? Maybe we don't solve all the challenges of a human being alive in space, but at least we make it a little bit better. But on the grand scale of things, much of what I just talked about doesn't require humans. Archinaut is a robot in space that builds big things for Earth. Making things in space that we bring back to Earth don't necessarily need an astronaut to do the making. It could be done robotically. The printers in space today are mostly controlled by Made in Space engineers, who some of them are in this room. So like the people actually building things in space are sitting in this room right now. And we teleoperate the printer. So we are already trying to do things in a way robotically because we believe that some of the biggest benefits that space gives us could just be the products. And we need to just make them there and bring them back and do it in a way where instead of polluting Earth, we can move our processes off of Earth.
There was a question of cost.
Oh, so the cost difference between doing it in space and... Oh, sure. Well, I mean, what we're looking at are things that you just can't build on Earth. There's, the optical fiber, for example, it can't be made to the efficiency that it could be made in space in a gravity field. So when you find products that just literally can't exist anywhere but if they were made off of the planet, that's the place to start because then cost isn't even the issue. Now, the cost to buy that fiber is something that actually already has proven markets on Earth at the numbers that it can be sold at. So it's not like you're making something that then you dangle over everyone's head and say, don't you wish you could have this? It's too expensive, right? I mean, you have to have a business model, you have to address costs, but we look at things that are beyond just that.
So with that, please join me in thanking Jason for an excellent talk. Thank you very much. Great talk.